Hello everyone, welcome again in my class. Today we will start module number 5. In module 4 we talked about interference, and in particular we talked about interferometers which give a fringe pattern by splitting its wavefront. Now from today onwards we will talk about interferometers which rely on division of amplitude. Now this is the whole syllabus of module 5. In this module we will talk about interference by division of amplitude, wherein we will talk about thin parallel films, then wedge shaped films, then the famous Newton's ring experiment, and very well known Michelson interferometer and its applications. For today we will cover interference by division of amplitude. I will talk about the concept here, and then we will go to a thin film wherein we will assume that only there are two reflected ray, and then we will talk about its interference and that conditions of maxima and minima. Now just to revive your concept, the interference pattern can be produced either by division of wavefront or by division of amplitude. This concept was introduced in prior lectures. Now whenever we say that division of wavefront, it means that suppose we have a point source here and it is emitting spherical wavefront, and then we put some slits in front of these wavefronts, spherical wavefronts, then what will happen? This wavefront will fall on these slits, and a part of this wavefront will pass through first slit and the part will pass through the second slit, and then from these slits new spherical wavefronts would be generated, and then they will propagate and interfere to produce interference fringes. And this typical example is utilized or seen in Young's double slit experiment. Now what is division of amplitude? In this particular case, the instrument divide the amplitude of the wave. How does it do so? Now as an example we can consider a thin film, and then suppose a light is falling here, a ray is falling on this film, then the part of the ray will get reflected and the part will get transmitted. This transmitted part will again fall on the second interface, and again a part will be reflected and a part will be transmitted. Now this reflected ray will again go back after reflection and a part will be transmitted, and therefore there would be multiple transmitted and multiple reflected wave, and these reflected and transmitted wave under suitable circumstances may overlap, and then they may give interference fringes. Now here you can see that a particular amplitude is being launched, and this amplitude is being splitted here. The part is getting transmitted and the part is getting reflected. It means the reflected and transmitted magnitude sums up, and then it gives the incident magnitude, provided the film is lossless. Such a splitting may also be observed in beam splitter. Now here we launch a beam of a ray. Now suppose a beam splitter has a semi transparent hypotenuse which is here, then after entering into the beam splitter, the part of the ray will be reflected downward and the part will get transmitted. The beam splitter is also amplitude splitting device similar to thin films. We will learn about this part of interference in module number 5. Now if a plane wave falls on a surface, of course this surface is assumed to be a transparent. We assume that there is a transparent film and the light or the plane wave is falling on the first interface of this transparent film. Then the some part of the wave is transmitted while some is reflected. Therefore, the incident amplitude is being divided in two parts. The first part is transmitted wave and the second is reflected wave, which is shown schematically here in this figure. Okay. The intensity I is lanced and the transmitted intensity is represented by IT and the reflected intensity is reflected by IR. If you sum these two intensity up, then we will get the original intensity, which is of I, provided the medium, the film, is lossless. Okay. And of course, the amplitude of the reflected and the transmitted waves are less than that of the original incoming wave. Yeah, this is the very simple concept, but we must understand it very properly. Yeah. Now, if a plane wave falls on a thin film, then the wave reflected from the upper surface interferes with the wave reflected from the lower surface, and which is can be easily understood from this figure. Yeah, wave is falling here, a part is getting reflected, part is getting transmitted, and at the lower interface again a part is getting transmitted and a part is getting reflected. Now, these two parts may interfere. Similarly, this ray may again get reflected here, and then several reflection and transmission may happen, and all this reflected ray may interfere and give some fringe pattern in this direction, and all this transmitted rays may also interfere and give some fringe pattern in this direction. Okay. And these fringes we often see in our daily life. Okay. Where do we see these fringes? The best example is formation of colors produced by a soap film illuminated by white light. Okay. Because whenever we use detergent, we see that soap bubbles get formed. Yeah. And these soap bubbles are very colorful. And what is the origin of these colors? This interference. Okay. Different component or different wavelength in white light, they interfere in different way or in different directions, and they produces their maxima at different angles, and therefore, we see different colors on soap bubbles. Yeah. Now, here we will talk about interference between two rays only, two reflected rays or two transmitted rays. Why only two? Because we assume that the reflection coefficient or transmission coefficient is such that the waves which beyond second reflection is very weak in intensity, and therefore, we assume that these rays can be neglected, the effect of these rays or contribution of these rays can be neglected. And of course, under this study we assume that the film is lossless. Okay. This interference is studied for a thin film which is assumed to be lossless, as I said, and the film is assumed to be thin because its thickness is of the order of wavelength. Okay. We have already discussed the relevance of word thin. Whenever we say thin, there is some reference thickness with which we compare it. Yeah. If the film's thickness is of the order of the wavelength, then only we call this film a thin film. Okay. Now, if a monochromatic wave is incident on such a thin film, then it splits into two waves of same frequency which have different amplitudes. Yeah. And these are shown here schematically in this figure. We have a point source which is situated at point S, and the ray starting from point source or a wave starting from point source falls on the first interface of this thin film. Okay. And the thin film has thickness d, small d, and refractive index Nf. Okay. The medium above the thin film has refractive index N1, while the medium below the thin film has refractive index N2. Okay. Now, when the wave strikes at point A on the first interface, a part of this wave will be reflected, while a part will go inside the film, which we call transmitted wave. Okay. This transmitted ray, it will again fall on the lower interface or the second interface of the film, and there again it suffers reflection or partial reflection and partial transmission. Yeah, this is the transmitted wave and this is the reflected ray. Okay. And similarly multiple transmission and reflection will happen, but here in this particular case we assume that only first two reflected ray contribute to the fringe formation, because the reflection and transmission coefficients are chosen such that further reflection and transmissions are so weak that they almost do not contribute to the effective electric field at the point of observation P. Okay. Therefore, we assume that E field is being launched, okay, and that reflected amplitude is represented by E1 R. This is the first reflected amplitude or the first reflected field. The second reflected field is represented by E2 R. Similarly, first transmitted field is represented by E1 T, while second transmitted field is represented by E2 T. Okay. We assume that the incident ray falls at angle theta I at the first interface and the angle of transmission is theta 2. Okay. Now, giving these conditions, we can now calculate the path difference between E1 R and E2 R. Okay. We will follow the traditional approach here. We will draw perpendicular from point C to point D. Okay. D is on ray E1 R. Okay. Now, this perpendicular will make an angle theta I with respect to the first interface. Here the path length after line DC is the same for both of the rays. Yeah. And here we put a lens, and this lens, what does it do? It make them overlap, it converges the rays, and therefore, these rays superimpose at point P, and where we are supposed to get interference pattern or fringe formation. Okay. Now, we will see, like now we will now talk about the path difference between the E1 R and E2 R. Okay. Then what is the path difference? Till point A the path length is same, and after line DC the path length is same. Therefore, whatever is happening, whatever difference is being created between the two paths is after A and before DC. Yeah. Now, you see that E2R, the second ray, is following path A, B, C, while the E1 ray is following path AD. Yeah. Therefore, the path difference would be this length minus this length. Okay. We will have to calculate the length A, B, C, and this is the usual length, but if you want to find the optical path length, then we will have to multiply this distance by NF. Similarly, we will have to multiply AD with N1 to calculate the optical path length for first ray, which is E1 R ray. Okay. Now, if to calculate the path difference, we will have to subtract these two optical path lengths. Yeah. And this is what is being done here. Yeah. The optical path length difference for the first two reflected beams is given by AB plus BC, which is nothing but this path AB plus BC. Yeah. This is the extra path which second ray is travelling within the film. Yeah. And AD is the path which the first ray is travelling outside the film. Okay. This is the AD, but to calculate the correct optical path, we will have to multiply these length with the corresponding refractive indices. And what are the corresponding refractive indices? In film, the refractive index is NF. Therefore, the path length which is inside the extra path which is inside the film, that has to be multiplied by the refractive index of the film, while the extra path for ray 1 which is outside the film, that has to be multiplied by the refractive index of the first medium, which is N1 here. Therefore, this difference will give us the optical path length difference, okay, between the two rays E1r and E2r. Okay. Now, from geometry, the AB is equal to BC and AB would be equal to, since theta t is known and d is known, the thickness of the film is known, therefore, AB which is equal to BC can be calculated using this trigonometrical relation, which is equal to d by cos theta t. Okay. Once expressions for AB and BC is known, we can substitute them back into the equation number 1, and from there we get equation number 2. Okay. Now, unknown quantity here in equation number 2 is AD. How to calculate AD? Let us go back into the diagram. AD is this length. Okay. Now, theta I is known, of course, AC is unknown, but we can calculate AC once AB is known and thickness d is known. Therefore, let us express AD in terms of AC, and this is the relation between AD and AC. Yeah. AD is equal to AC sin theta I, and theta I is here, this angle. Yeah. Now, AC is unknown, how to calculate AC, and theta is the angle of incidence. Suppose we want to represent everything in terms of theta t, then we can use Snell's law. Okay. And what is Snell's law? Now, you see in this figure, sin theta I upon sin theta t is equal to NF upon N1. Okay. If this is known, then from here we can get the expression of, you see here, we want to expression of theta I, then theta sin theta I is equal to NF upon N1 into sin theta t. Yeah. Therefore, we can replace sin theta I by NF by N1 into sin theta t, and this is what is being done. Yeah. Sin theta I in equation number 3 is replaced with NF by N1 sin theta t. Okay. Once it is done, the next unknown is AC. Yeah. Now, from the figure itself, AC is equal to 2d tan theta t. Yeah. AC is this distance and B is situated here, and this is your d, okay, and this is theta t. Using very simple trigonometry, we can calculate that AC is equal to 2d tan theta t. Yeah. This is nothing but this part of the diagram. Yeah. Now, there is no unknown quantity now. We can substitute the expression of AC into equation number 2. Both AD is replaced with this expression and AC with equation number this expression 2d tan theta t. This ultimately give us the expression for optical path length difference, which is represented here by capital lambda, cap lambda. Okay. Now, bit of simple mathematics will give this very simplified expression for this optical path length difference, and which is equal to 2 NFD cos theta t. Okay. NF is the refractive index of film, d is its thickness, and theta t is angle of transmission. Okay. The first transmission. Okay. Now, once the optical path length difference is calculated, we can easily calculate the corresponding phase difference. How to calculate the phase difference? Just multiply it with k naught. What is k naught? K naught is free space wave number. Okay. And this is what is being done here. Yeah. This is the corresponding phase difference, k naught into cap lambda. Okay. But apart from these this phase difference, there would be some additional contribution. Okay. What is that contribution? The additional contribution would be because of the different nature of reflection involved here. What are different nature of reflection? Here one reflection is internal while the other is external. Okay. What is the difference? Now, you see here in this figure, the ray is falling here at the first interface and then it is getting reflected. Yeah. This is happening at the first interface, while the transmitted rays, they gets in and then they get reflected back and then transmitted back into the first medium. Now, if the film is kept in air, then the first reflection is happening here and the second reflection is happening here. It is similar to the case where we are having one interface, here it is first medium, it is here it is second medium, and first reflection is happening like this, while the second reflection is happening like this. Okay. This is similar to the concept which we discussed while studying optical reversibility, and optical reversibility says that R1 is equal to minus R2. Okay. It says that between external and internal reflection there would be a phase difference of pi. Okay. And this is why in this case also there would be an additional phase shift of pi. Okay. That has to be taken into account while calculating the conditions for maxima and minima. Okay. Therefore, the total phase difference would be equal to k naught into cap lambda, sorry it is cap lambda plus pi or minus pi, yeah, we can choose any, either plus pi or minus pi. Okay. Now, let us substitute for the expression of cap lambda, then we get 4 and k naught is equal to 2 pi by lambda naught, and after a bit of simplification this is the expression for phase difference. Okay. The sign is immaterial, and therefore, let us pick one particular sign, and here we pick minus because this gives a bit simpler expression. Okay. Now, we are talking the reflected light here. The reflected light, in reflected light an interference maximum will occur when the phase difference is equal to integral multiple of 2 pi. Okay. Here m is equal to 0, 1, 2, yeah, it is an integer. Yeah. Therefore, maxima occur at p when the phase is equal to integral multiple of 2 pi. Now, let us substitute the expression of this phase difference from equation 9 in here with a minus sign before pi. Okay. If you do this after a bit of rearrangement, we get this condition. This is the condition of maxima. Okay. This is the condition of maxima in reflection. Okay, where m is an integer and lambda f is equal to lambda naught by nf. Okay. Lambda is the wavelength of light in film, which differs from the wavelength of light in vacuum. Okay. Now, once the maxima in reflection is known, we can calculate the condition of maxima and minima in transmission too. What would be the difference? Let us go back into the first figure. In this figure, you see the first reflection is external one. Now, this ray is getting transmitted, and this is giving a field of magnitude E1 to E1t. This is the first transmission, and second transmission is E2t. In transmission, the first ray or first beam is not suffering any reflection, while the second while in second transmission the first reflection is here and the second reflection is here. These reflections are internal. Okay. These are happening within the same film. Okay. The conditions are the same. Okay. It is happening from film to the external medium, and this one is also happening from film to the second medium. Yeah. The interface is of same nature, provided these two mediums are the same, N1 and N2 are equal. If this is the condition, then the extra pi shift in phase which we considered for the reflected light, that can be neglected. Okay. It means the same condition, this condition of maxima would be condition of minima in transmitted arm. Okay. Why? Because we will have to take away pi, the extra phase shift, because now the reflection which is involved here are both internal. Okay. they are occurring on same type of interface. Okay. Therefore, this previous relation also correspond to minima in the transmitted light. Okay. Now, once the maxima is known, let us calculate the minima in the reflected light. How to calculate the minima? The phase should be 2m plus minus 1 pi, okay, that is odd multiple of pi. And if you simplify equation 8, then you get this condition, and this is minima condition in reflection, and which also correspond to maxima condition in transmission here, and this means maxima in transmission. Okay. And similarly here this correspond to minima in transmission. Okay. Now, there is two special cases. What is this special case? If the refractive index of the first medium is larger than that of the film, and that is again larger than the refractive index of the third medium, or if the refractive index of the first medium is smaller than the refractive index of the film, and which is again smaller than the refractive index of the third medium. In both these cases, this phi phase shift will not appear, it would not be present. Okay. And therefore, the relations, the condition of maxima and minima in transmission and reflection would be modified. Okay. This equation would be different, because now we will have to take away the pi phase shift, the extra pi shift phase shift from equation number 10 and 11. Okay. Now, this is the basic concept, like and this is the very simple example of an interferometer which work on division of amplitude. Yeah. And this is all for today. See you all in my next class. Yeah. Thank you.